Well, hello and welcome to Stars, Cells, and God. This is the show where we discuss new discoveries taking place at the frontiers of science that have theological and philosophical implications, as well as new discoveries that point to the reality of God's existence. My name's Jeff Zweerink, and I'll be your guide today as we explore our topics. But before we get into the discussion, I want to encourage you to subscribe to our channel, Reasons to Believe. Click on the bell icon so you can be informed of new videos. Learn more at reasons.org or by following us on social media at RTB_official. Well, let's get into it today. Hugh, I'll let you go first. I know you have some discussion on a particular type of exoplanet, so go ahead and tell us what you got.
I think this is kind of up your alley, Jeff, so this should be fun. If you can think back a couple of years ago, well, maybe 3 years ago, there was a huge internet buzz about how they found phosphine in the upper atmosphere of Venus.
Yep.
Phosphine being a rather good biosignature, and they said, we think we find bacteria there.
Right.
Well, what happened is over the past few months, subsequent months, they said, we made a mistake. We overestimated what we saw, and the claim is now completely withdrawn.
Well, so the phosphine's there, but it's just the biological origin of it, or is the phosphine even gone?
They basically said we can't claim that we found any phosphine
Okay.
in the upper atmosphere. Because a couple of other independent teams said, let's see if we can find the phosphine. They couldn't find it. The original team redid their data and said, we made an analysis error here. And so it's been withdrawn. Well,
I will say that's often the way science works. That's the whole point of publishing it. I've noticed that with science being in the news a little more, people see these little arguments go back and forth, and it seems to degrade their confidence in the reliability. But this is the way science has always worked.
It's the way science works, but it's not the way the internet works.
That's a fair point, yeah.
Because, when this phosphine announcement came out, there were literally dozens of articles saying, hey, astronomers have found life in the atmosphere of Venus. You didn't see anything about the claim being withdrawn.
Right.
You do see it in the scientific literature, but it didn't show up on the internet.
Yeah.
And so I got concerned when 2 weeks ago there was an announcement made, hey, we found dimethyl sulfide in the atmosphere of an exoplanet about 100 light years away. And on Earth, dimethyl sulfide is produced by marine organisms, especially by phytoplankton and algae. In fact, they produce about 10 million tons per year.
And my recollection, that wasn't just, we found dimethyl sulfide, it's we found a life-bearing organic molecule. It was far more... or at least in the popular
the popular literature, the focus was on the dimethyl sulfide because they said on Earth that only comes from the emission from marine organisms, and therefore there must be marine organisms on this exoplanet that's producing this stuff. And when you read the paper, they're actually claiming, well, we may have found a second biosignature, the chloromethane. That didn't get into the popular literature.
Right.
But again, I counted over a dozen articles on the internet saying, hey, this is a major breakthrough.
Right.
And then I looked at the research paper, and it's been accepted for publication, but it's still going through the peer review process.
Right.
So I basically got the preprint and read the preprint, and what I noticed was they definitely had found methane in the atmosphere of this exoplanet.
That's a pretty exciting find in and of itself.
It is, but they're finding methane in the atmosphere of quite a few planets.
Yeah.
And it can be a biosignature because there's methanogens on the Earth that produce methane, but there's lots of abiotic ways you get methane. There's methane on Jupiter, Saturn, Uranus, and Neptune. And, that's all explained by abiotic process.
Well,
Moreover,
part of the fascination with methane is that it's not a particularly long-lived molecule.
Right.
So the fact there's got to be some continuous
way of
mechanism of it. But I think you're right. There's known abiotic and biotic ways of doing that.
Well, especially for this planet, because it's not like Jupiter, Saturn, Uranus, and Neptune. It's orbiting close to its star.
Okay.
The closer you are to the star, the more rapidly you got to replace the methane because the light coming out of the star basically dissociates methane in the upper atmosphere.
Right.
So, and this particular planet they're talking about, and that was curious to me too, because I looked at the internet articles, it wasn't giving a lot of detail about the star or the planet, but the paper did.
Right.
Basically said it's orbiting an M3 dwarf star, which means it's a cool, small mass star. And to get it in what they call the liquid water habitable zone, the planet has to be orbiting quite close.
Right.
In this case, it is. It's orbiting 40% the distance that Mercury orbits the sun. So
that's pretty close, yeah.
It's pretty close, yeah. It's about 6 times closer than the Earth orbits the sun. And that's good because the star is quite dim, and so you're going to need it orbiting very close to put it in the liquid water habitable zone. That was part of the thing that was on the internet. Hey, it's got liquid water, maybe.
Yeah.
And so that might fit the biosignature. And then the planet's mass is 8.6 times the Earth's mass, and it has a density of 2.67 grams per cubic centimeter. And that's why the authors...
How does that compare to the Earth's?
Well, the Earth has a density of 5.5 grams per cubic centimeter.
Okay, so this is noticeably less dense than the Earth.
Much less dense.
Right.
And much more massive. And so they referred to it as a sub-Neptune, which I think is accurate.
Right.
And, they have what they call super-Earths and sub-Neptunes. They both come in at, say, 5 to 10 times the mass of our star, the sun. The difference is a sub-Neptune has a low density, whereas a super-Earth, they typically classify it as having a high density, meaning it could be a rocky planet.
Something akin to Earth, then.
Something akin to Earth, whereas this is more akin to what you see in Uranus and Neptune.
Gotcha.
And so that's the background for this. And when you actually look at the molecules that they discovered, they came in with methane with a signal that was 5 times above the noise. And, that's what we astronomers would classify, that's a detection.
That's a detection, right, yeah.
Yeah. Everything else was way below 5 times above the noise, including the dimethyl sulfide. What shocked me is that they had 2 models to explain the signal that they saw of dimethyl sulfide. One had a 1 sigma effect.
Okay.
The other was 2 sigma, which means we're talking, maybe once above the noise, or a signal twice as great as the noise. And I saw you smile. It's like when you got a result or detection that's at the 1 or 2 sigma level, it's like it's not going to get published. Yeah,
well, that's what's weird. I mean, you just look at the statistical significance of that, and I'm going to draw a blank on the exact numbers, but I remember, a 1 sigma detection. It basically says that out of 100 of these, 66% of these are going to be noise, and you have a 66 or 68-ish% confidence level that this is not noise, which is pretty small. Yeah. And I loved you talked about it being 5 sigma, and there's a reason why that's there, and I don't know how dispersed this is across the astronomy community, but I know in gamma ray astronomy where I worked, there were a whole slew of 3 and 4 sigma detections back in the 70s and 80s that we found these sources and these sources, and we've come to find out that none of them were sources at all. And so that's why that 5 sigma is there, is to keep you from getting really excited about stuff that was noise.
This takes me back to my graduate school days, because I actually found several 5 sigma sources in my radio observations. I didn't publish any of them.
Oh, yeah?
And the reason why, I was doing 1,500 hours of observations a year. And if you're doing that intense of observations, the statistical probability that you'll come up with 5 sigma events that are simply noise, I mean, if you're observing over a 5-year period, you're going to get 1 or 2. And I was only getting 1 or 2. Now, I did publish one where I had 7 sigma.
Yeah.
I said 7 sigma, even with all the observing I'd done, that's a legitimate discovery.
Right.
And so I did publish that, but the 5 ones I didn't, because there were several times where I saw a signal 5 times above the noise. I went back a month later, tried to find it again, wasn't there.
Yeah.
So it's like, okay, that was simply noise. And an analogy I think lay people understand, think about surfing. you ever watch surfers? Here in California, we have a big surfing community. What you do is you see them out there on their surfboards, and they're waiting. And they know that if they wait for 10,000 waves, they're going to get one where the wave height is about 4 times higher than the average.
Okay.
And then they ride that wave in. They get a really good ride.
Yeah.
But you got to wait a long time. You got to wait for, on average, about 10,000 waves to go by. But that wave that's 4 times above the average wave height, it's noise.
Exactly, yeah.
Yeah, it's not something, well, gee, we got a tidal wave coming in because there's an earthquake. No, it's just noise. And where you're looking at that much data. And this is interesting because they also claim we detected carbon dioxide in the atmosphere. And I looked at the level, and it's 3 times above the noise. Now, a layperson looks at that and says, well, that's a 99.7% chance they've got a positive detection. I think that's a real detection. But I mean, if you're looking at 1,000 different spectral lines, 3 of them are going to be showing up at 3 sigma, and they're going to be pure noise.
Well, again, that just kind of surprises me because that it gets published. I mean, I see the methane there, and I do actually see the interest in the paper. I think it's an interesting result. Whether it's a detection or not, just the level of what you're finding kind of warrants, hey, even if it's you just say, hey, tentatively, we think we found this. I think that's important. So not minimizing that. The idea that it's been so widespread is, I mean, this idea behind the 3 and the 5 sigma detections, that's been around for decades, and scientists know that. How that got translated out into all the public stuff, or how we prevented that, or how we didn't keep that from getting so big in the public literature is a little bit odd to me because we know what's going on there.
Well, for example, what all got all the public attention was the dimethyl sulfide.
Right.
So I looked at the paper, and they had 2 different models to try to explain the level of detection. And one model said, well, it's at a 2 sigma level. The other one said it's at a 1 sigma level.
Right.
But the most likely correct model is the 1 sigma one.
Right.
And it's like, you're actually saying that you got a possible detection where you only got a 1 sigma signal? That seems utterly absurd.
Right.
I mean, and so I'm wondering, how did this get published? Well, it hasn't gone through the peer review process. It wouldn't surprise me they say, take this out.
Yeah. No,
but they do make the point in the paper. I mean, I do admire the authors because they said, this is a possible detection. It needs to be confirmed with additional observations. It's the James Webb Space Telescope that found this. And they said, and so I think they published this with the idea, let's use this as leverage to get more telescope time on the James Webb and see if we can really get a high signal to noise. Because, I mean, their observation, they didn't get a lot of time on the telescope.
Right.
And so they say, hey, we're seeing this thing. Let's go back and check it out because this could be really interesting because this seems like a really definitive biosignature. And then when they looked at the chloromethane, I read through the paper and they didn't even try to come up with an analysis of the detection level. They just said it wasn't as high. So it's actually below 1 sigma for the chloromethane. And they weren't pushing that anyway because we've actually found chloromethane on a comet. We found it in a molecular cloud, and in both cases, we know that the chemistry of we know that the chloromethane has to be produced by abiotic mechanisms because it's a place where clearly there's no possibility of life. And so chloromethane we now know is not a good biosignature. Dimethyl sulfide, and I've checked into that too. The reason why people say, well, on Earth, all the dimethyl sulfide comes from, marine organisms. It's because they pump out 10 million tons a year. They're pumping out a lot, so much so you can smell it when you're at the beach. It's the smell of rotting seaweed or whatever.
Oh, that's what that smell is. Okay.
Yeah, that smell, it's dimethyl sulfide.
All right, okay.
But because it's 10 million tons per year, you can actually detect it quite easily. But you actually can get dimethyl sulfide without life, just that you're not going to get that huge of a quantity. You're going to get
Yeah, no, that makes sense.
They're going to get small quantities.
Well, so I was, just because I saw the title, I was kind of curious what all that was, because I remember hearing this discussion about the potential biosignatures, if you will. It did seem like, two questions that rose up. One, it seems like there was an interest in this planet independent of the biosignatures because it has this new class of planet, this Haitian.
Right.
I think that's actually in the title of the paper. That's why I went and looked up what it was, that it's this ocean-covered, thick hydrogen atmosphere type planets that are that are predicted to exist. And so this was an example of that. So I'm curious your thoughts on that aspect of it. But then the other part is, okay, so I'm with you. I don't think this rises to the level of, okay, we've detected some really interesting biosignature here. But I'm curious, what are your thoughts if we actually do find this in reality? What does that mean?
My major critique of what these people published is they shouldn't be referring to this, hey, we may have detected life on this planet, because the very characteristics of the planet rule out the possibility of life.
Okay.
And so we know if the dimethyl sulfide actually stands up to being a real detection, it's got to be produced by some other means. Same thing with the chloromethane shows up. It's got to be produced by some other means. We know we can make a lot of chloromethane without life. It's really challenging to make a lot of dimethyl sulfide without life. But the very fact that the planet has characteristics that rule out life.
Well, why couldn't you have? I mean, if you've got a liquid water environment with a thick thick hydrogen atmosphere, what is it that rules out some sort of primitive cellular life in the oceans? That doesn't seem that extreme of a stretch.
They looked at they said, okay, if our methane definitely is going to stand up, but they said if our carbon dioxide measurement proves to be real, not just a 3 sigma signal, but 5 or 6 sigma signal, that would indicate that the atmosphere of this planet, K2-18b,
right,
would be thin. And so they came up with this model, which you refer to as a Haitian model, where you've got a sub-Neptune with a thin hydrogen atmosphere and a really thick ocean underneath it.
Right.
And you need, and the idea of
this is like thick ocean, as in many, many, many times deeper than what our ocean is. Our oceans are here on Earth, am I correct?
Thousands of kilometers.
Yeah, that's
not
like
4 or 5 kilometers,
exactly.
but thousands of kilometers. So you got this deep ocean. And my initial comment is, well, that's interesting, but that's only going to be the case if the carbon dioxide measurement stands up.
Okay.
Because if the carbon dioxide measurement doesn't stand up, that means you've got a thick atmosphere. With a thick atmosphere, you're going to get greenhouse heating.
Why does the thick atmosphere? Because the moment you've got methane and water, you're going to get that reacting and getting carbon dioxide. That doesn't seem like such a stretch to me.
Well, what they also came up with is we got non-detections. We found no water in the atmosphere of this planet.
Oh, really? Okay.
No water at all.
Okay.
No carbon monoxide.
Okay.
No ammonia. So the fact that you're missing ammonia, carbon dioxide, and water, and you got methane at a high abundance level, and hopefully, they said, for their model, lots of carbon dioxide, that would imply you've got a thin atmosphere and a thick ocean water.
Okay.
So it remains to be seen if that model stands up. Now, in some respects, I think it's reasonable. A sub-Neptune that's 8.6 times the mass of the Earth, when it forms, it's going to have a really thick atmosphere.
Right.
But as it migrates in towards the star, and if the migration happens early and it's fairly aggressive, I could easily see the early because M stars, when they're really young, they're pouring out a very strong stellar wind. And it can be up to 100,000 times stronger than the sun's wind. And so that wind is going to sputter away the atmosphere. So I can imagine in that scenario, starts off with a thick atmosphere, comes in towards this star, and in the youth of that star, it would transform the thick atmosphere into a thin atmosphere. So I'm okay with
making
that.
something like a Haitian planet doesn't seem...
It's not unreasonable.
Yeah, right.
I don't think they've proven it,
right.
But they've indicated it's reasonable. Okay. The issue I have with this, I think I got a slide on this, so let's see if we can pop the slide up. That just shows you the molecules. That's dimethyl sulfide, and that's chloromethane.
Okay.
But this is the model of the Hycean planet.
Right.
So what you got is a thin atmosphere, a thick ocean, and then you got the silicate iron crust. But notice I show an ice layer around it.
Right.
And what got overlooked by these authors is a paper that was published back in 2014.
Okay.
This paper is 44 pages long. I didn't copy the whole thing.
Right.
It's a thick paper, but it's a very interesting paper, and I've written on it before, which basically demonstrates if you've got liquid water that's more than a few hundred kilometers deep, and in this case we're looking at thousands of kilometers deep, you're going to get permanent ice at the bottom of that ocean.
Right.
Because of the pressure. And we all know that ice floats in liquid water, and you don't expect ice to be at the bottom of our ocean. That's because our ocean's not thick enough.
Right.
Make it thick enough, the pressure of the liquid water forces a different kind of ice to form at the bottom. And as this paper published back in 2014 points out, these Hycean planets cannot possibly be life-bearing planets because you've got this permanent ice layer that isolates the liquid water from the rocky material.
So presumably you're not going to get any sort of dissolving of the materials, the nutrients that
you're
any
not
sort
going
of
to get
life
the
would
chemistry
require.
that life requires. You're not going to get the chemistry that the origin of life requires.
Right.
And so what these authors said back in 2014, these Hycean planets where you got a thin atmosphere and thick water, they're not going to be life-bearing planets because of this ice barrier that prevents any kind of chemistry for the origin or survival of life. Now, if you go with a really thick atmosphere, which is what happens when you've got a Neptune-type planet that doesn't get so close to its star that the star sputters away the atmosphere, that atmosphere is going to trap heat from the star, which means that the liquid water will become steam. So, and either way, if you wind up transforming all the water to steam, you got a problem because water is a greenhouse gas. The more water you turn into water vapor, the more heat that gets trapped.
Well, but if you're talking 1,000 miles or 1,000 kilometers of water, you're not going to get all that into steam. It seems like there's going to be some region in there where you're still going to have liquid water. Would you end up getting rid of the ice layer? Is there a scenario in there where you're going to get rid of the ice layer where you're actually going to get the chemical mixing that
you get rid of the ice layer if you can boil off a huge amount of the water, but you got to be boiling off like 95% of the water.
And then in that case, it seems like you're going to have an incredibly dense atmosphere.
Yes, and it's going to be really hot.
Exactly, yeah. So that's going to be problematic for life in its own ways.
My whole point, Jeff, is no matter how thick or thin the atmosphere is, it rules out the planet as a candidate for life. If you got that much water, whatever form it's in, liquid, vapor, or ice, you got a problem. Now, I'm confident that they're right, that we're dealing with a water world here. That's a term that astronomers use for a planet that's got way more water than the Earth has. But I think what I see in this paper and what I see back in 2014, water worlds where we got over, say, 300 kilometers thickness of water, they're not candidates for life. So
well, and I find these sorts of things interesting. I mean, yes, we've spent a lot of time talking about how this can't be a place that hosts life. I would agree there. I do think a lot of these investigations are just kind of fascinating because I mean I think I can make a pretty strong argument that part of the reason that Big Bang cosmology is such a sound theory out there is that people have spent so much time thinking, oh, this might work as a way to whether show that God doesn't exist or show that the universe doesn't have a beginning or does have a beginning, that there's been so much investigation of it that we're very confident that it is the correct picture. I kind of see a lot of this in that same class. I mean, this is a fascinating, hey, can we find places where life might exist? And hey, maybe there's these kinds of planets where life might exist. So I think that's pretty fascinating. But the more we study, it seems that's what actually provides the evidence that allows us to decide what's really true and what's going on out there. So I think this is a really cool thing.
The reason I wanted to do this for Stars, Cells, and God is that they end their paper by saying, Hycean planets. however you want to pronounce that.
I think it's, believe it or not, I read up, I'm like, what in the world is a Haitian planet? It's a combination of hydrogen and ocean. So I think it's Haitian planet.
Haitian planet, okay, good. They make a big deal at the end of their paper saying, these are the candidate planets we need to look at to find life.
Right.
And so they're saying these are really excellent things, but they've overlooked the ice problem. And they've overlooked the problem of what happens to the atmosphere.
Well, and they've also overlooked the problem. Well, I don't know, it's a problem. They may not actually exist. We predict that. I mean, we found all the other kinds of planets. We haven't found this particular type. It's a prediction that it does exist, but we haven't found them yet.
Well, they're basically saying in this paper, we think that this particular
Right.
planet is the best candidate for this
Exactly,
category of planets. I'm persuaded that these planets really do exist. I mean,
It makes sense to me.
given
yeah.
that there's lots of water in the universe,
Exactly.
and given that there's lots of Neptune-type planets,
Right.
they should exist.
Yes.
So I'm confident they exist. I'm not confident that they're candidates for life at all.
Mm-hmm.
The other thing that struck my attention, thinking back to the phosphine excitement of 3 years ago, is that, and I remember talking to Sarah Seeger about this, and we met her at the Origin of Life conference, and she's mentioned here is that she's probably the one astronomer that's done the most work on biosignatures.
Mm-hmm.
And I think what's coming out of all this, you can't look at a single molecule as a biosignature.
Right.
If there's really life on the planet, you're going to see multiple biosignatures. Because, life produces not just one molecule.
Right.
Produces phosphine, it produces dimethyl sulfide, produces methane. And so you need to look for a family
Right.
of biosignatures because no single biosignature by itself is definitive. They were thinking, well, dimethyl sulfide is as close as you can get. I think I agree with them. It's probably the best biosignature we can think of.
Mm-hmm.
But even that shouldn't stand by itself. We need to have multiple
Right.
biosignatures.
Well, that's what they've been talking about with methane. I mean, when they found the Martian methane, that was one of the, hey, maybe this is an example. I've heard that a lot of people say if we find both methane and free oxygen, that would be a really good indicator of life. Not because any one of those is unique. It's that both of those are incredibly reactive. So if you have a little bit of oxygen and a little bit of methane, they're going to react. But you've got to have some sort of source of those that continually produce them, and so those might be it. But to your point, you got to have both of them around, and so
there are ways you can get planets with both oxygen and methane on it without life, and so you really want to have like 5 or 6.
That makes sense.
Yeah,
yes.
rather than, but I do. In fact, I remember talking to Sarah Seeger, and she says ozone is a much better biosignature than oxygen. And I think she's right about that.
That makes sense, yeah.
And ozone's easy to detect.
Right.
Much easier to detect than oxygen is.
Mm-hmm.
So, and hey, I'd say we need to keep looking because even if we rule out all these planets, it's going to tell us a lot about the design of Earth that makes life possible here on Earth.
I couldn't agree more. So, any other comments? Or
no, I'm good. So what?
Well, very good. I want to switch over and talk about a paper that was recently published in the Astrophysical Journal.
Oh, yeah, I remember that one.
And this is, I'll just show it. It's the JWST Hubble sequence, the rest frame optical evolution of galaxy structure at redshifts of 1.5 to 6.5. And
first of all, tell us what a Hubble sequence is, because that's...
I will get to that.
Okay.
And what just the context of this is that since the James Webb Space Telescope has been up, there's been a lot of discussion about the types of galaxies they've found, and we're finding these well-formed or disk-type galaxies that shouldn't be there. And so there's just a lot of discussion of that. And this is a paper in that vein. And to your point, you were talking about galaxies, and so this is the paradigm of how astronomers think about galaxies.
That's what they teach you in freshman astronomy classes.
Exactly. That there were different kinds of galaxies. There's elliptical galaxies. Those are the ones kind of off on the left there, the E0. You could measure the ellipticity. The ones that are balls are E0. The more elliptical they get, the higher the number they get. Then you get these S galaxies, which are spiral type galaxies, and they branch out into, it's called the Hubble tuning fork is one of the names given for it. Is you've got some where there's a bar that the arms kind of come off of, and others where the arms just kind of come out of the bulge itself. And so for a while, astronomers thought that maybe the ellipticals evolve into the spirals. And all of this is to say is that there's lots of different kinds of galaxies we see. We have this classification now where we look in our local neighborhood and we can find that there are quite a few spiral galaxies. There are a lot of elliptical galaxies, and we kind of know what they look like. And what astronomers have been trying to do is say, all right, as we look back in time, how do we get galaxies to form the way they are? And one of the things that had come out of the measurements by the Hubble Space Telescope and a lot of the telescopes up to that time is there's this picture where galaxies early form. They're small, peculiar, odd, irregular galaxies, and you just have a bunch of mergers over time, and eventually you build up into these larger structures. And as these larger structures happen, you can get spirals, and there's just a long, kind of drawn out process that produces these larger spiral type galaxies. And just to kind of give an example of the structure in those, as we've looked at our galaxy, which is the one we can study in great detail, you think, okay, you got the Milky Way, and you can show this is a great picture taken by a satellite that went up above the top of the galaxy. No, I'm joking. We don't have, this is a simulation or a composite of our data put into a picture to make it look like that. And I'd make that joke just so that you're careful to know what's actually imagery and what is a
reconstructed map?
Reconstruction. And because that's getting increasingly hard to tell, and not everybody is so careful about making the distinction. But we've got a central disk in our galaxy, or a central bulge. There's a bar, some level of bar there, and you've got these spiral arms in there, and you can see it's all, the blue is, that's where new stars are being formed. They give off very blue light. You can see these clusters of red light. That tends to be signatures of old stars. And so if you kind of put all that together and say, what is, in a schematic form, what's the structure of our galaxy? You've got the center of the galaxy, which is a massive black hole, something on the order of a couple million times the mass of the sun. There's a bulge of stars around that. There's a disk, but a disk that is made of two components. There's a thin disk where most of the spiral arms are, and then there's a thicker disk which has a different class of stars in there. And then you've got these globular clusters scattered throughout this larger halo, which are also a different class of stars. And then in the halo, throughout all that halo, there's a pool of dark matter that all this is happening in. And so astronomers are working to say, okay, how does all this form? Because each of these stars, or each of these components of the galaxy have different types of stars. The stars were formed earlier, stars were formed later, some are more massive, some are smaller. They're clustered together tightly, they're more dispersed. And so the question is, how do you get all of this structure? And again, this led to that picture that the early in the universe, you're going to have small, irregular, not well-defined galaxies, nothing with this kind of structure to it, and this is going to develop later as these galaxies evolve. What's interesting about this paper, and I'll just show the abstract out of the paper and highlight one particular comment that I think is interesting, and then I have some questions for you because there are some apologetic implications that flow even beyond this. But the abstract ends with this. It says, we compare our results to theory to show that the fraction of types of galaxies, these irregular spirals, ellipticals, that we find is predicted by cosmological simulations, and that the Hubble sequence, this tuning fork diagram, was already in place as early as 1 billion years after the Big Bang. And to me, what I find exciting about this is that we had this idea. We said, okay, we know there are galaxies. We know that if you go back early enough, you've got the cosmic microwave background radiation, which gives you a picture of how clumpy the universe was at the time. And you say, all right, that picture from the cosmic microwave background radiation has to grow into the galaxies we see. And the question is, how does that happen? And we had some ideas. That's where you get this, you've got these smaller galaxies coalescing and growing larger and merging, and eventually you make these bigger spirals. seems to me what this study is showing is that that picture is incorrect at some level, because these larger galaxies, which we thought took long times to form, actually are there very early in there. And what I find exciting about that is that it says, all right, our simple, well, we've got the seeds and they just grow and become this, isn't right. It's actually a more complex, more sophisticated mechanism to go from the cosmic microwave background to the galaxy structure we see. And I would expect in that, because it's not just in going back to your comment, it's not just, this is the noise, this is the way things happen. Yeah, there are some large things that, large waves that show up. It's all noise in the ocean. The fact that it's not just, this is the way it grows, that there's a more sophisticated process going on. I'm expecting that as we understand that process, which we didn't even have the tools to know was true until James Webb went up, that we're going to find a lot more design in that. Because we clearly need spiral galaxies, but there's mechanisms at play there that we haven't sorted out that produce these spiral galaxies very quickly in the universe. And I think we're going to find a lot of design as we now have tools to probe this region where we couldn't. We're going to see a lot of design in there.
I think you're right, and I like the fact that you say this is complicated, because I remember going back to, say, in the 1950s where they produced this Hubble tuning fork, and there was a lot of agreement amongst astronomers saying there's actually an evolution of galaxies going on. There was actually two schools of thought back then. Spiral galaxies evolve into elliptical galaxies.
Right.
The other one, elliptical galaxies, evolve into spiral galaxies. But they had this idea that there was some kind of evolutionary path.
Right.
But even before the Hubble Space Telescope went up, we had big enough telescopes saying it's not that simple.
Right.
And the problem is, unlike the stars that are far apart, even in galaxies are relatively close together. The universe is only 13.8 billion years old. And the farther back you go in time, the greater the density of galaxies. We would expect things to be messy.
Right.
And I think James Webb is basically telling us it's even messier than what we thought with the Hubble Space Telescope.
Right.
And so, because, we do look early in the universe, we see a lot more spiral galaxies than we see today. Something must be going on that causes the spiral galaxies to collapse and become spherical ellipsoidal galaxies. On the other hand, we do see galaxies merging together where you wind up getting a big spiral galaxy as a result. And so the dynamics of galaxies, and given how close they are together, we would expect things to be messy. And I think the surprise from the Hubble Space Telescope is these galaxies form relatively intact spiral structures quite early. That shouldn't come as a shock, because we know that the spiral structure of our galaxy has been stable for 11 billion years.
Well, that to me, at least in my misconceptions, when I first started getting into apologetics or kind of understanding how things work, my impression was, okay, water is critical to life. And as we look around our solar system, we don't find a lot of water. Now, I mean, we do know that Enceladus has some, and we know that, Europa has, that's actually the most abundant one, probably. But to me, the idea of finding water on a planet was, okay, that if you find water on a planet, that's going to be a good sign of life being there. I've come to realize that water is an incredibly abundant molecule.
Right.
That the standard feature of a rocky planet is that it starts off with water. What's remarkable is that Earth still has its water, because both Venus and Mars probably started out with similar amounts of water. Mars, clearly it was liquid. Venus, there's a question of whether it was ever liquid or not. But nonetheless, both of them had equivalent quantities or proportionate quantities of water. But 4 billion years later, Earth is the only one that still has abundant liquid water and a stable water cycle. It's the longevity that actually is what's remarkable about Earth, not that it has water in the first place.
Well, I think that's also true of our Milky Way galaxy. It's its longevity that makes it so exceptional. And part of it is, with advancing telescope power, Because I remember as a grad student thinking, well, our Milky Way galaxy has had a stable spiral structure for 6 billion years. And the date kept getting pushed back.
Okay.
In fact, when I put out Design to the Core, I said 10 billion years.
Right.
A few months after that book was published, another paper came out saying, no, we need to push it back to 11 billion years.
So it's just affirming this is not a startling result in some sense. It is that these galaxies, like the Milky Way, in some sense, the spiral structure, have been around for a long time.
Well, basically what we're realizing with our Milky Way galaxy, it had to be spiral by the time the universe was 1 billion years old.
Right.
And it got bigger through merger events, retained its spiral structure.
Right.
But for the last billion years, its spiral structure has remained undisturbed, which is highly unusual.
Right.
Given the density of galaxies, it's really extraordinary that we haven't had a major bump from a small galaxy, whereas Andromeda had one just 500 million years ago.
Right, yes.
We've gone 11 billion years without any significant event. But as you look at other galaxies in the universe, we're realizing they get bumped a lot. And if they get bumped a lot, we're not going to be able to have this nice, clean tuning fork picture.
Right, exactly.
That's obviously that's oversimplified.
Of course, yes.
But what is interesting, I think you're bringing out, is the attempt to build a Hubble diagram in the early universe has the potential to expose just how complex things are in the early universe. Let's compare what's going on in the current universe. Maybe we're going to learn something.
Absolutely.
In fact, one article I'm going to be writing up for my blog is the fact that James Webb found that stars and galaxies in the very early universe are nowhere near as efficient at making heavy elements as we thought they were.
That's interesting. Yeah, I'd like to see that. I do. Rather than get into that, since you're going to talk about it later, I do have one more, and I'm going to frame it in a gotcha question. So one of the comments, if I go up a little bit earlier, we find a strong dominance of morphologically selected disks, like spiral-type galaxies, up to z equals 6, which is about 1 billion years after the universe was formed. In this mass range. We also find that the stellar mass and star formation rate densities are dominated by disk galaxies up to that time, demonstrating that most stars in the universe were largely formed in a disk galaxy.
Yeah.
Now, one of the early, I want to say probably Creator in the Cosmos, it may have been Fingerprint of God, but I think it was Creator in the Cosmos. You give a list of, here are the types of, our star needs to be in a spiral-type galaxy. You say most spiral-type galaxies are some fraction, most of them are elliptical or irregular. And my recollection was it was like 97% of galaxies are not spiral, or 97% of stars are not spirals. I may be remembering the number incorrectly.
Yeah, what I did write in the first edition was that measurements were showing that in the current universe, only 6 or 7% are spiral, whereas in the early universe, about 2/3 of them are spiral.
Okay, all right. Yeah, so that goes to my question is, walking away, and I walked away with that thinking, okay, you've got to have spiral galaxies. Spiral galaxies are fairly rare. How do we do apologetics where we're talking about stuff that's kind of on the edge of the research, but allow people to not set it up so that Christianity looks weird or wrong if we say things incorrectly? Because if you were to walk away from that saying, well, it's got to be a spiral galaxy are rare, most of the stars are not in a spiral galaxy, if that becomes a support for the Christian faith and you come to find out later, now very clearly, that spiral galaxies are pretty abundant and may be dominant throughout the universe, how do you do apologetics in a way so that you're not conflating something kind of on the cutting edge of our research with the stability of what Christianity has said?
Yeah, well, I mean, even back then we were saying the population ratios vary over the history of the universe. So the spirals are way more common in the early universe than they are in the current universe. The latest literature is saying it's not as rare as only 6 or 7% being spiral. The number is actually bigger than that. Mainly because they looked at all the irregular galaxies and have now classified them as spiral. So in the old days, we had 3 categories. You got the spheroidal ellipsoidal galaxies, the spiral galaxies, and the irregular galaxies. You probably remember when you were an undergraduate, the Large Magellanic Cloud was classified as an irregular galaxy. It's now classified as a spiral galaxy.
Right, okay.
So the whole point is, you know, if you're using different definitions, it's going to change the numbers.
So it does seem like there's just some level of apologetics. We need to be careful when we're dealing with science and supporting Christianity. I think science has a great deal of support for Christianity, but how we do that, we need to be a little
for
just
example,
circumspect.
I think one factor we need to be looking at is, okay, we have all these spiral galaxies. There's a big difference between tiny ones like M33 and ones like M32, the Andromeda Galaxy and the Triangulum Galaxy. Maybe we need to be more careful about classifying these spiral galaxies, especially since we're throwing all these irregulars into the pile.
Yeah.
And so you're talking about the Hubble tuning fork. I think we're at a point in astronomy where we need to come up with a much more complex tuning fork than what we see back from the 1950s.
So it's a good introductory tool
It's
to
an
get you out to
introductory tool.
recognize there's a lot more detail we know now that we didn't know.
We know
that.
now,
that's a good
and
point.
I think it's going to show us details about the universe. I think it's going to strengthen our design argument because now we have a much more detailed picture of what's really going on with galaxies. But I think it's also important. We need to realize that tuning fork changes over the history of the universe, and the James Webb is going to reveal what's really happening, say, in the first 5 billion years.
Well, I appreciate that. So why don't we go ahead and wrap the show up? I want to thank you for joining us today and encourage you to join the discussion in the comments below. Remember to like this video, subscribe for more content. New episodes of Stars, Cells, and God release each Wednesday and are available here on YouTube and on your favorite podcast app. Be sure to share this video with friends, and remember, the more we know about science, the more reasons we have to believe.